Hey everybody, we're live and in stereo. So now we're going to look into the 2024 set for Organic Chemistry Introduction. This is chapter number 11 as of now. And without further ado, let's just jump into the questions and see how difficult organic chemistry questions and MCQs really are, which you have been taught to be scared of since ages now, right? Since the start of time. Chalo, let's start. So it's saying geraniol and nerol, I couldn't care less what they are isomers of each other. Okay, they are isomers, I should care. Which type of isomerism is shown here? So if you look at both their structures, it's ditto. This structure, same to same, this bond, all the bonds are ditto, but as you see and move through the structures, you realize, hey, there's something that's changed between these two. Look at this fella. This is carbon double bonded to carbon right here, and this carbon is bonded to CH2OH, but here the carbon is bonded to hydrogen, and the CH2OH is right here below this double bond. This is right here and this is right here, right? So what do you see? Do they have different structural formulas? No, the structural formula is the same. If the position of the bond is above or below this plane, it doesn't really matter. The structural formula is the same. What it indicates is that they are probably what? They are geometric isomers, and if you see whether they satisfy the condition of geometric isomers, they absolutely do. Each carbon in the double bond is bonded to two different groups or two different group of atoms. See, this carbon is bonded to a CH3, and this entire fella, this carbon is bonded to this and hydrogen. So each carbon in the double bond is bonded to two different groups, and therefore this will exhibit geometric isomerism. And these are what? These are cis-trans isomers of each other just by looking at their spatial arrangements, right? And if you wanted to figure out which one is cis and which one is trans, for this particular example, I've taught you guys priority, which is not part of your course to much extent. But if you want to figure out which one is cis and which one is trans, since higher priorities in this case are on opposite sides. See, this one has more atomic numbers, this one has more atomic numbers compared to these two. Obviously you can see them with your naked eyes. So between this and this one has the higher atomic numbers. Between this and this one has a higher atomic number sum. So since higher priorities are on opposite sides, this fella is the trans version for it, and this fella is the cis version for it, because higher priorities in this case are both on the same side. See, this fella is the higher priority stuff, this fella between these two is the higher priority stuff. So they are on the same side. On the same side, there's the Z version of it or the cis version of it. Obviously you don't need to know this, but you just need to know that does it show chain isomerism? No, there's no variation in the chain. Does it show position? No, chain and position are both examples of a structural isomerism, right? And in this case the structural formula is ditto. And geometric and optical, if you want to check out for optical, whether optical isomerism exists here, any carbon must have four different groups of atoms bonded to it, and no carbon is exhibiting that. Maybe you say, hey, this carbon is bonded to different group of atoms, but they are not four, they are three. 1, 2, 3. So you realize that optical isomerism in fact does not exist, and the only option you're left with is geometrical. Done. B is the correct option. Next question. Which compound has the greatest number of stereoisomers? Now for this you also have, because we know that stereoisomers are both optical and geometrical, we have to make them. So 2-methylhexane, those who are pathetic with naming and who don't know their naming stuff, they will fumble here because they won't be able to make the structure. So that's why namings are very important. Now how do you make structures out of names? Always first make the parent chains. This is my advice to all of you. If you want to make your life easy and not make your life a living hell, always make the parent structure. So it's hex 2-ene, right? So 2, 3, 4, 5, 6. Hex means 6 carbons, and 2-ene means that the double bond must be between the second and the third carbon. So in all these cases the double bond is between the second and the third carbon right here. So again, 2, 3, 4, 5, 6. Sorry for my pathetic drawing. 2, 3, 4, 5, 6, and the double bond is right here between the second and the third carbon. And let's just duplicate that. So in all these cases, let's just duplicate and duplicate, right? So this fella and this fella, these are my 4 options that the examiner has given to me. The only difference is the first fella has methyl on the second carbon. So if you start counting from the left to right, obviously we'll start from left to right because the double bond is closest to the left. If I start counting from here, the methyl is on the second carbon right here. 1, 2, 3, 4, 5, 6, right? So first draw the structures. Here the methyl is on the third carbon. So 1, 2, 3. This is where the methyl is, right here. Next, the methyl in C, the methyl is on the 4, I'll call this C. So in C, the methane is on the 4th carbon. This is 1, 2, 3, 4. This is where the methane is, right here. And use yellow here. Done. And this is A, B, C, and let's look at D. In D, the methane is on the 5th carbon. So let's start numbering. 1, 2, 3, 4, 5, 5, 6. The methane is on the 6th carbon right here. Now, out of these, which one will have the greatest number of stereoisomers? Now, for stereoisomers, we have to look at both geometric and optical. Now, if you look at the first fella, does it exhibit geometric? Let's see. The first carbon double bond, it has a CH3 right here and a CH3 right here. So this carbon has the same group of atoms. The carbon which is in the double bond has the same group of atoms bonded to it, which means that this fella cannot exhibit cis-trans isomerism or geometric isomerism. Although this carbon is bonded to a hydrogen and this entire fella, they are different, but this fella is bonded to a CH3 right here and a CH3 right here. See, if you want me to show it to you, this is actually a CH3 and that's actually a CH3. So this will not exhibit geometric isomerism, right? No geometric isomerism. And what about optical? It can't exhibit optical because if you look at the carbons which aren't in the double bond, if you look at this carbon, this carbon, this carbon, they have hydrogen, hydrogen. It's like a CH2. It's bonded to two hydrogens, right? Along with these groups as well. So it needs to have 4 different groups, not the same. And you see that since this carbon is bonded to 2 hydrogens, obviously, two of the atoms are not of the same type. They are not of this, not of different groups. They are of the same group, right? Or the same group of atoms, which is hydrogen, 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 hydrogen. So these are all CH2s, and therefore this will not exhibit optical as well. So neither optical nor geometrical. A में तो कुछ भी नहीं है ना. In A you neither have optical nor do you have geometric isomerism. Done. No cis-trans, no geometric. Let's look at B. B, and obviously when you guys are doing this in the exam, it will take you not more than 30 seconds to do it. I have to explain it to each and every student in a lot of detail, so it'll take me more time, but for you guys it should be less than 15 seconds to figure out which one will show you the greatest number of stereoisomers, right? Now if you look at these two fellas, in this particular case, let's see whether it would exhibit geometric isomers. If this carbon is bonded to a CH3 and it's bonded to a hydrogen, because we don't show hydrogen bonds in skeletals, right? And we have only shown 3 bonds, so the 4th must be with hydrogen. So this is a CH3 and hydrogen. This carbon satisfies cis-trans. Let's look at this carbon. This carbon is also bonded to a CH3 and is bonded to this entire group of atoms. So it means that this will exhibit cis-trans isomers, right? So this will exhibit cis-trans. But if you want to look into optical, if you want to look into the optical isomerism, each carbon, you must have a chiral carbon, or the carbon must have 4 different groups. This carbon does not have 4 different groups. This carbon does not have 4 different groups. This carbon does not have 4 different groups. You might think, sir, what about this carbon? This carbon has 1 different group this, 1 different group this, and 1 different group this. It does not have 4 different groups. It has made a double bond. Double bonds will never show optical isomerism. Why? Because in double bond, you can't even satisfy 4 different groups. You will have a maximum of 3 different groups, if any, right? So cis-trans isomerism can only happen, and you will have 2 isomers here, because one will be the cis version and the other one will be the trans version. So B has 2 isomers. Let's see if others have more than 2 or less than 2, because B can potentially be my answer if these 2 have 0 isomers, but probably that's not the case. Let's check out C. So we come to C. Check it out. Does C show geometric isomers? Now you should be quick with it. Yes, this carbon is bonded to a CH3 right here and is bonded to a hydrogen. So this carbon satisfies the geometric isomerism idea. And this carbon is bonded to this entire group of atoms and is bonded to a hydrogen. So this also satisfies the geometric isomerism idea, and therefore this will exhibit cis-trans or geometric isomerism. Done. And if you look at all the other carbons, does any other carbon exhibit optical isomerism? Absolutely. This 4th carbon right here, it is bonded to a CH3. It is bonded to this entire group of atoms, is bonded to this entire group of atoms, and the 4th bond is not shown, which is obviously with hydrogen, right? If you want me to show it to you, this is the 4th bond. So it's bonded to a CH3, a hydrogen, and this group of atoms and that group of atoms. So it's a chiral carbon. I can even put asterisk here. This carbon is a chiral carbon. It's a chiral center. It will exhibit optical isomerism. It'll give you 2 enantiomers, which are non-superimposable images of non-superimposable mirror images, right? So this particular fella will exhibit optical. So you have cis-trans and optical, which means how many stereoisomers would you have? 2 to the power of 2, which gives you 4. So I probably think that C would be the correct answer. B is wrong now because B only exhibits 2. This exhibits 4. Next, let's look at D. D, in this case, do you have optical isomerism and do you have stereo do you have optical isomerism, and do you have geometric isomerism? Let's check it out. Well, if you check out D, you have cis trans, obviously, because this carbon is bonded to two different group of atoms. One is bonded to the CH3 and one is hydrogen. This carbon is bonded to this entire group of atoms, and the other one is hydrogen, which I have not shown. This is basically the trans version of it, right? So this will exhibit cis trans isomerism. And now a lot of you might think, sir, what about optical? Let's check this out. This carbon will not exhibit optical isomerism. This carbon, you might think it exhibits optical isomerism because it's bonded to this group of atoms, it's bonded to this group of atoms, this group of atoms, and one hydrogen. But sir, use your eyes. Don't make me, call my friend who is an ophthalmologist to help you guys check your eyes, because you realize that this is a CH3 and this is also a CH3. So these aren't different group of atoms. They're both what? This is CH3. And this line is also CH3. So understand that this carbon cannot be optical because it's not bonded to four different group of atoms. It's bonded to CH3 right here. Yes, hydrogen is different and this entire stuff is different, but these two are both CH3. So this is not optical isomer, and therefore the option that you end up with is C. Bas, that's it. These are organic chemistry MCQs. What's difficult about it? If your concepts are clear, everything should be crystal clear in your brains. Next. Compound X is found in cell walls of some bacteria. Its structural formula is shown. Okay. How many stereoisomers are there with this structural formula? So he's given you this long ass structural formula. He's saying how many stereoisomers are possible. Stereoisomers again can be of two types. Optical, I'll have to keep my I have to be vigilant for optical, as well as geometric. So optical and geo. Let's see. For geo, I'll have to look into the double bonds, right? So here you have a carbon-carbon double bond right here. You have a carbon-carbon double bond right here. And if you check this out, this carbon is bonded to a hydrogen and is bonded to these group of atoms. So they are different groups that this carbon is bonded to. So this checks out right here. And if you look at this carbon, it's bonded to a hydrogen and is bonded to this entire group of atoms. So which means that cis trans isomerism will exist here because each of the carbon in the double bond is bonded to two different group of atoms, two different groups or two different group of atoms, right? So this will exhibit cis trans, absolutely. This is cis trans. Done. Next, so you have one fella that will exhibit cis trans. Now I don't have any other double bond, so I'll have to look into what? I'll have to look into chiral centers. I'll have to look into carbons which possibly are bonded to four different group of atoms. So this carbon, not four different group of atoms. This carbon, not four different group of atoms, is two hydrogens. This carbon is in the double bond, so can't be chiral. This carbon is in the double bond, can't be chiral. This carbon isn't bonded to four different group of atoms because of two hydrogens. This carbon right here, check it out. This carbon is bonded to a hydrogen, and in the brackets you have OH, which means the OH is on top or on the bottom of this particular carbon, right? It's like this. Carbon is bonded to a hydrogen and it's also bonded to the OH right here. Carbon is bonded to a hydrogen, and in brackets the OH is given in brackets, which means that this OH is bonded to this particular carbon. So carbon bonded to hydrogen, bonded to OH, and it's this carbon is bonded to this entire fella, and this carbon is therefore bonded to this entire fella. So this does absolutely give off a chiral center. See, this carbon is bonded to this carbon is bonded to all of this, and this carbon is bonded to a hydrogen, and this carbon is bonded to the OH, right? So there are four different group of atoms that this particular carbon is bonded to, therefore making it a chiral center. Done. Now moving on, any other carbon. This carbon right here, this carbon is bonded to a hydrogen, is bonded to a CH3, is bonded to a CO2H, and is bonded to this entire group of atoms. This entire group of atoms. If you want me to show it, you see, this carbon is bonded to a hydrogen, and in brackets you have CH3, so it's bonded to CH3 right here. It's bonded to CO2H, and it's bonded to this entire group of atoms. All of these atoms right here, OH, CH, all of these atoms, I'll call this R. So this in fact is also a chiral carbon. So how many isomers would this exist? You have 1, 2, 3. Plug it in the formula, 2 raised to the power 3. That gives you 8 stereoisomers, and D is therefore the correct option. Right? And those who don't like formulas, you guys can use possibilities as well, and I've taught those possibilities in my life class, RRR, RSR, RSS, and so on and so forth, right? You guys can check that out. Next. Structural isomerism only should be considered when answering this question. Structural isomerism should only be considered when answering this question, okay? Now he's saying how many straight chain isomers are there with molecular formula C4H8Cl2. So he's saying only give me the structural isomers, but don't give me the stereoisomers or whatnot, right? So C4, you have 4 carbons. Let's use Arcan method. Let's use Arcan method. 2, 3, 4, 2, 3, and then tuck and tuck. Obviously, we normally ignore these two. Done. So 4 carbons, 2, 3, 4. What are my add-ons? My add-ons are 2 chlorines, right? So first I'll put the chlorine right here. See, I'm adding a Cl right here, and I'm adding both the Cls on the same carbon. This is what I'm doing. Now what I'll do is I'll fix the position of one Cl, and I'll start to shift this Cl to this one, this Cl to this one, this Cl to this one right here. So I'm going to fix the position of the first one, 2, 3, 4. This is Cl, and I'm gonna move all the others, right? I'm gonna move all the others. You just have to come up with possibilities. Done. And this, I move all the other. Let me just duplicate this fella. Tuck, tuck, tuck. I see. So in the first case scenario, I've done this. Now I have fixed this fella, and I'm moving this Cl, tuck, tuck right here. So I'm going to move the first Cl to this particular place, then I'll move it to this particular place, and then I'll move it to the end. This is good stuff. Now what I'm going to do is I'm going to change something else now. See, I've made 4 different options, but now instead of fixing the Cl here, I can fix this. I can take this Cl out and fix it over here on this particular top right here. And then I will move this Cl to this Cl to this Cl to this, right? And that's the only 2 possibilities that can take place. So I'll fix a Cl right here on the second carbon. And now I will start to move the Cls, right? So this is the first Cl, 2, 3, 4. I will fix it on the second carbon. I'll move this Cl right here to the second one, 2, 3, 4. This Cl has been fixed on the second carbon. This is 2, 3, 4. And I'll fix the Cl on this particular carbon. There are a lot of duplications here. You'll see the duplications, right? And I'll plug it in here, right? So these are all the possibilities in the first case scenario. And obviously, I'm gonna cut out all the duplications from it, right? So this is the first idea. If I look into the 3 chain fella, 2, 3 chain fella, what can I end up with? I can put the Cl on the first carbon. I now have a CH3 as my add-on, and I have 2 Cls, right? So I know I first have to add the CH3. So I'll add the CH3 right here, because if I add the CH3 right here, it's already been discussed right here. If I add the CH3 right here, it'll increase the length of the carbon chain, already discussed right here. So now I will just keep on adding my Cl. So I'll add the first Cl on the first fella, and the first Cl right here on the first fella, as is, right? I add both the Cls here. Then what do I do? 2, 3, tuck, and I add the Cl right here. Then 2, 3. I've added only 1 Cl here, right? I have to add what? I have to add 2 Cls. So add it, please. Add it for me. Okay. So I added the Cls. Everything is good and goody. Now let's see where duplications occur and what is the reality of things. Chalo. This is 1, 1. The first fella is what? 1, 1. Dichloro meth eth pro but. So dichloro. First one is 1, 1 dichloro. Done. The second fella is what? The second fella is 1, 2. So it's 1, 2 dichloro, right? So these two are different. 1, 2 dichloro butane. Done. Next, the third fella, 1, 2, 3. 1, 3 dichloro. This is also different. The fourth fella, 1, 2, 3, 4. It is what? 1, 4 dichloro. Done. This fella right here, it is what? 1, 2 dichloro. And we've already discussed 1, 2. So these two are the same. I'm going to cancel this fella out because it's already been discussed right here. 1, 2. This is also 1, 2 dichlorobutane. Done. Let's discuss this. Which fella is this? It's 2, 2 dichlorobutane. And this fella, 2, 3. See, 1, 2, 3. 2, 3 dichlorobutane. And now let's start numbering this fella right here, because the Cl is closest from the right to left. So this is what? 1, 2, 3, 4. And this fella is what? 1, 3 dichlorobutane, and we've already discussed it right here. 1, 3 dichlorobutane. So this fella is obviously also discussed, right? So now how many straight chain isomers do you have? 1, 2, 3, 4, 5, and 6. Sir, but what about these? These are also isomers. These are also isomers right here. These are also isomers, but are they straight chain? The answer is no. He's saying how many straight chain isomers are there with C4H8Cl2. I just wanted to draw it to show it to you that this can also possibly exist, but he wanted the straight chain isomers, right? So you have 1, 2, 3, 4, 5, 6, and therefore A is the correct option. Absorb, please. Okay, moving on. So we're done with this fella. Obviously, these two also did exist, but they are branched. They're not straight chained. I have to teach you all the aspects for it. What is true for every nucleophile? It's saying every nucleophile should attack the double bond. So nucleophile is nucleus loving. We know that. Nucleophile means nucleus loving, which means it should attack positive stuff, not negative stuff. Double bond is a high electron density. Electrophiles will attack it, not nucleophiles, so A is wrong. It donates a lone pair of electrons, and yes, this is true for all nucleophiles, and you learn that even later on, that all nucleophiles do donate a lone pair of electrons. It is a single atom? No, it's not, because we've studied that in introductory classes that cyanide can also act as a nucleophile. Cyanide can act as a nucleophile. It basically bonds, and I've shown it to you in the last class that we took for organic chemistry, last introductory class. So no, it's not necessary that it must be a single atom. It can be the hydroxide ion even. It can be a lot of other ions as long as it has the lone pair. It is negatively charged? Not necessarily, because you understand, you'll study that later on even, that ammonia is neutral. H2O is neutral. It has no charges, but since it has lone pairs, only that is the reason why it can act like an electrophile. It can still be attracted or make love to the positively charged substances because it has lone pairs. So it's not necessary that it has a negative charge, but what is necessary is that it should have a lone pair. So D is also wrong. The correct option therefore is a Biarino. Done. Next, sodium chromate. What is this question doing here, yaar? This is not an organic chemistry question, but hey, sodium chromate 6, which means it has an oxidation number of +6, is manufactured by heating chromite FeCr2O4 with sodium carbonate in an oxidizing atmosphere. Chromite contains these ions, the Cr2O4 2 minus ions. If you want to figure out the oxidation number here, let's figure it out. You have Cr, which is X, but you have 2 of those. Oxygen is -2. You have 4 of those. Add them together. The overall oxidation number of any ion is its charge, which is -2. 2x minus 8 equals -2. 2x equals +6, and x equals +6 divided by 2, that gives me +3. So Cr here is +3 in this case, and added Cr here is +3, and Cr here he's already told you is +6 from this Roman numeral, right? So you went from +3 to +6. And if you look at iron is +2 here. How do you know iron is +2? Because see, it's very common sense. Cr2O4 is 2 minus, and you are only requiring 1 iron for it. So for Cr2O4 2 minus to be only requiring 1 iron, that means iron must be +2. +2 would balance out this 2 minus. That's why 1 iron ion is required for the Cr2O4 ion, right? Similarly here, if you look at this fella, it's Fe2O3, and if you take the charges back up, it's basically what? Iron had a charge of 3 plus O was 2 minus. That's why when you cross multiplied, you got Fe2O3. Or you could say, hey, you have 2 iron ions and 3 O2 minus ions. So see, 2 times 3 is 6 plus, and 3 times 2 is 6 minus. So the charges balance out right here. So iron must be +3 here. Iron went from +2 to +3. And so what you realize is, since iron went from +2 to +3, there is an increase in oxidation number. Iron is therefore oxidized from this fella to this fella. The Cr went from +3 to +6, therefore there is an increase in oxidation number, and therefore this fella is also oxidized. You went from +3 to +6, so there's oxidation happening here, there's oxidation happening here. And so it's saying what happens in this reaction. Chromium and iron are the only elements oxidized. That is absolutely true, because if you look at oxygen, it's in its pure elemental state, which is an oxidation number of 0. It's not combined with any other element, but oxygen here is -2. We know oxygen is -2 except for in peroxides, which is -1. So in all cases, oxygen is -2. Went from 0 to -2. So oxygen is being reduced, and carbon's oxidation number is the same. It is +4 here, and you can check out it's +4 here, So it doesn't matter. See, you can even calculate it. Carbon is X. We don't want to waste our time here, but so carbon is X, oxygen is minus 2, times it by 2 because you have 2 oxygens. So X minus 4 equals 0, X equals plus 4. Similarly here, it's the carbonate ion, CO3 2 minus ion. You can calculate carbon here. Carbon is X, oxygen is minus 2, times it by 3. You have 3 oxygens, add them together. Overall oxidation number of an ion is its charge. X minus 6 equals minus 2, X equals plus 4. So carbon did not change. So that's why chromium, carbon is not oxidized. Carbon is the same. Chromium is oxidized. No. Iron is also oxidized. Iron is only oxidized. No. Chromium is also. This is not an organic chemistry question, by the way. I don't know what it's doing here, but it's here. Next. The diagram shows the skeletal formula of citric acid. What is the molecular formula of citric acid? Come on, this is a piece of cake. A piece of, just count the number of carbons. Let's count it. 1, 2, 3, 4, 5, 6 carbons right here. So C and D are wrong because you don't have 8 carbons or 10 carbons, you have 6 carbons. Now count the oxygens. 1, 2, 3, 4, 5, 6, 7. See, 7 oxygens in A, 7 oxygens in B. So I just counted A and B. Doesn't really make, and I couldn't even care less about the oxygen. See, when you eliminated 2 options, the way you should now select between these 2 is what's the change here. Carbon is 6, carbon is 6, O is 7, O is 7. So I don't even have to count O and waste my time. I just look at the hydrogens. Here you have 8 hydrogens, here you have 4 hydrogens. Which one is correct? See, you have 1, 2, 3, 4 hydrogens, therefore B is wrong. Why? Because he has not mentioned about the hydrogens which are also present here. So you don't even have to count it. You have to just say, hey, examiner, you are missing out on these hydrogens right here. You don't have 4 hydrogens, you have 5, 6, 7, 8 hydrogens in totality, right? So once you counted out 4, you said, hey, the examiner has made a mistake here. He's not counted this hydrogen, so don't even need to count it. Ke yaar ye 8 hai ki nahi. You don't even have to count it. Just 4. Okay, he has missed out these hydrogens, so B is wrong. A is the correct option. These are the tricks that you need to use in MCQs to quickly solve them, or you'll be stuck spending hell lot of time on these MCQs. A section showing 2 repeat units of an addition polymer is shown. What is the identity of the monomer that produced this polymer? So the monomer that produced this polymer, you haven't studied alkenes yet, so I'll just show you. This is the monomer, right? What happens is that this bond folds back up, this bond folds back up, and you get a double bond right here. This is how you figure out the monomers. Well, you learn that later on in alkenes chapter, but this was probably, I put it here because you have studied polymerization in O-level IGCSE. That's probably why I put it, but you'll study it later on, right? You just fold these bonds back up and you get a double bond right here. So tell me, what is the name for this fella? Just tell me the name. 1, 2, 3, 4. Select the longest carbon chain. It's 1 carbon, 2 carbon, 3 carbon, 4 carbon. 4 carbon is what? Butene, because it's an alkene, it's butene, but put the position of the functional group which is between 2 and 3. So it's what? Butene. And on which carbon do you have the chloro and which carbon you have methyl? You have chloro on the second carbon and methyl on the third carbon. So it's 2 chloro because C comes first before M. So it's 2 chloro, 3 methyl, butene. Do you have 2 chloro, 3 methyl, butene? Absolutely you have. It's not butane. That's why A is wrong. C doesn't make sense. It's not pentene. It's not, you selected the longest carbon chain. It's of 4 carbons, not of 5 carbons. And this fella that they have written is to confuse students. You might think that, you had to name this entire thing, but you have to only name the monomer, not this entire fella. These are just chains being repeated. So those who circled this probably were naming this entire thing. You just had to name the monomer, not this entire thing. Sorry, D is wrong. Done. Again, if your concepts are clear, I haven't done these MCQs beforehand. I'm doing them with you guys for the first time, but I know these answers are correct, because your concepts need to be clear. In which pairs are both species free radicals? Now, free radicals are species with unpaired electrons. And so I have to check out which of these species have unpaired electrons. And the way I can do that is look into their electron inbox diagrams, right? Because I'm given too many options, so I'll have to look into their electron inbox diagrams to figure out which one of these species have unpaired number of electrons. Let's check it out. Chlorine has 17 electrons and 17 protons, obviously. And O has 8 protons. Therefore, for an O atom, you must also have 8 electrons, right? So let's check it out. If I put the periodic table here, I'm going to use help from my periodic table. Where is my periodic table? I'm going to take help from it to write down the electronic configuration quickly. In the exams, I'll do the same. This is my periodic table. I have to figure out the electronic configuration of O, and I have to figure it out for Cl. I'll first write the subshell electronic configuration, which is what? O is what? Helium, 2s2, 2p1, 2, 3, 4. So it's helium, 2s2, 2p4. That's what O is. And if I look at Cl, Cl is what? Cl is neon, 3s2, 3p1, 2, 3, 4, 5. So neon, 3s2, 3p5. That is what chlorine is, right? Now, if I look into their outermost electrons right here, the p electrons, by the way, I can check out their electron inbox diagrams, right? P4 means what? You have one electron here, one here, one here, and then the fourth electron goes here. And you already know why this happens, right? All the principles come into play. You've studied this in chapter 2. So this is how you show the electron inbox diagrams, and it has unpaired number of electron, which means what? That O is therefore a radical species, right? It's highly reactive even. And if you look at chlorine, the 3p fella, because the 3s2 is already filled, I don't even have to look into it, right? This 3s2, this 2s2 is already filled. Tuck, tuck. I don't even have to look into it. So 3s2 is already filled. I'm just going to look into 3p5. This is 1, 2, 3, and the fourth and the fifth electron go here. So this fella is unpaired, and therefore it is a radical. So both chlorine and oxygens are, both Cl and O in this case, are radical. What about Cl1 minus and O2 minus? If it's Cl1 minus, that means what? That instead of having 3s2, 3p5, now you have one extra electron. What do you have? You have 3s2, 3p6. And if you check out 3p6, this is 1, 2, 3, and all these electrons are now paired. So Cl1 minus is not a radical. It's not. It has paired electrons, right? And if you look at O2 minus, O2 minus means what? That oxygen has gained 2 electrons. So now it's going to be not 2s2 and 2p4. It's going to be 2s2, 2p6. And 2p6 means that all the electrons are tuck, tuck, tuck. All electrons are filled. They are all paired. So this fella is also not a radical. Cl and O minus. Now Cl we already know is a radical because we checked it out above. O minus. O minus means that instead of being 2s2, 2p4, now you've gained an electron, so you're 2s, 2p5. And 2p5 means what? 1, 2, 3, and then 4, and then 5. You still have an unpaired electron. Unpaired electron right here. So that means what? That this fella is also a radical. So 2 and 3 both are, Cl and O minus both are radicals. What about Cl plus and O2 plus? Cl plus means that now you are not 3s2, 3p5, you have lost an electron, so you are 3s2, 3p4. And if you want to see 3p4, it's 1, 2, 3, and the fourth electron is paired right here. So you have unpaired number of electrons. Therefore, the Cl1 plus is also a radical, highly reactive species. Done. And O2 plus, sir. O2 plus. O2 plus means what? That you are now not 2s2, 2p4. You are what? You have lost 2 electrons, so you are 2s2, 2p2. And 2p2 means what? It means 1 and 1. Unpaired electrons. So this is also a radical. Done. So this is how you had to look into this. So 1, 3, 4, A is the correct option. Now there's an easier way to do this. There's a shortcut to do this. Do you want to see the shortcut way? Do you want to see the shortcut way? It'll take you 2 seconds. If you're short on time in the exam, you should go for 1, 3, and 4. And why? Why should you go for 1, 3, and 4? Remember, whenever you want to look into radicals, this is the proof for it. I did not want to give you guys the shortcut directly. I wanted to prove it to you, and then I'll tell you the shortcuts in the exam. If you want to look into the idea which one would be a free radical, you know free radicals are highly reactive. They normally don't exist in that state, do they? They normally don't exist in that state. They are highly reactive. They are unpaired electron, but highly reactive. They don't normally exist in that state. Now you tell me, does Cl exist in the form of Cl, or does it exist in the form of Cl2 in the universe? Or O exists in the form of O or O2. We know that Cl exists in the form of Cl2, O exists in the form of O2, and they are both the same as they are shown in the periodic table. So these are radicals. They have unpaired electrons, right? So these two are both radicals. Done? That's fun. When you want to check these two out, these two are the stable ions for it, right? We know that Cl makes the Cl1 minus ion, O makes this 2 minus ion, and therefore their octet rules are being followed. So if the octet rules are being followed, that means that you don't have any unpaired electron. You don't have any uneven or unpaired electron. Therefore, these two can't be my radicals, right? And so if you look at O minus is pretty strange, isn't it? O minus is pretty strange. O minus normally doesn't take place, which means what? Which means that this is radical. O minus, normally we have O2 minus or we have O. We don't have O minus, do we? Which means this would be highly reactive and it would either go into O or it would go into O2 minus. So this probably is a radical, right? So this is how you do it in the exam if you don't have time. Cl plus, normally we don't see Cl plus. See O2 plus, it's pretty strange. We don't see O2 plus. We don't see Cl plus, we don't see O2 plus in our day-to-day lives, do we? So if you're short on time, you can go for 1, 3, 4, tuck. And that's it. This is if you are short on time. Other than that, you do this. And you won't be short on time if you quickly go through these ideas. Done? Next. In the general formula of which class of compounds is the ratio of hydrogen atoms to carbon atoms the highest? One, it's a piece of cake. Alcohols, what's their general formula? CnH2n plus 1 OH. What's the general formula for aldehyde? CnH2nO. What's for carboxylic acid? CnH2n plus 1 COOH. Haloalkanes is CnH2n plus 1 X, which is a halogen atom. Now just plug in 1. See, if I plug in 1 here, how many carbons do you have? You have 1 carbon. And how many hydrogens do you have? 2 times 1 is 2, 2 plus 1, 2 times 1 is 2, 2 plus 1 is 3, and 3 plus 1 is 4. So you have hydrogen to carbon atoms, H ratio C. You have 4 H's to 1 C in an alcohol. If you put 1 here, you can put any number. I'm just putting 1 because it's easier. If you put 1 here, you have 1 carbon and 2 hydrogens. You have 2 hydrogens for every 1 carbon right here. If you put 1 here, what will happen? If you put 1 here, you'll have 2 times 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So you have 4 hydrogens for every how many carbons? 1 here and 1 here. You have 2 carbons. So 4 hydrogens for every 2 carbons, which makes it into 2 ratio 1. And if I put 1 here, what does that give me? If I plug in 1 instead of n, that gives me, you have 2 times 1 is 1, 2 times 1 is 2, 2 plus 1 is 3. So 3 hydrogens for every 1 carbon. So if 3 hydrogens for every 1 carbon, which ratio is the highest? It's 4 ratio 1 right here. A. Done. Next. Compound T has the skeletal formula shown. Which is the structural formula of compound T? Try it on your own. It's a piece of cake. Let's see. Let's try it. See, if you start checking out the longest chain, it is 1, 2, 3, 4, 5, 6, 7. This is the longest chain. 1, 2, 3, 4, 5, 6, 7. This is the longest chain. And I can even write 1, 2, 3, 4, 5, 6, 7. Now, let's start to highlight the longest chains here. 1, 2, 3, 4, 5, 6, 7. That's the longest chain because 1, 2, 3, 4, 5, 6. This will give me 6, right? So I had to go down. 1, 2, 3, 4, 5, 6, 7. This is the longest chain. Now let's highlight the longest chain here. This is 1, 2, 3, 4, 5, 6. Oh, this is 6, not 7. 1, 2, 3, 4, 5. What's happening? So the longest chain here is incorrect. If you start highlighting it, it'll either give you 1, 2, 3, 4, 5, 6, or it'll give you 1, 2, 3, 4, 5, 6, or it'll give you 1, 2, 3, 4, 5, 6, or it'll give you 1, 2, 3, 4, 5, 6. So it does not have any 7 long chain. It has 6 carbons as the long chain. So the molecular formula is not the same. Hence, this is incorrect. Let's look into C. And we can also number this, right? You start numbering from where the alkyl group is the closest. So instead of starting numbering from here, you start numbering from here because the first alkyl group is closest here. So what do we call this? This is 1, 2, 3, 4, 5, 6, 7. Done. Similarly here, 1, 2, 3, 4, 5, 6, 7. And this is incorrect. Why is this incorrect, guys? Why is this long chain incorrect? Is this the correct long chain that I have selected? See, it's 1, 2, 3, 4, 5, 6, 7. But you can also have a long chain that looks something like this. 1, 2, 3, 4, 5, 6, 7. Which one should I go for? Should I go for this long chain or should I go for this long chain, the one that I have already highlighted in yellow? Here, the naming convention comes into play. You know, if there's a tie between parent chains, I've taught you guys this, right? If there's a tie between parent chains, which one do you go for? You go for the parent chain with more substituents. So I'm not going to select this because this has this one big ass substituent. I'm going to go for this 7 because then it'll have 1 substituent, 2 substituent, 3 substituent. Here, you just have 2 substituents right here. So this is the incorrect version of it. The long chain should not be this. Rather, what should it be? It should be this 1, 2, 3, 4, 5, 6, 7 right here. And you start numbering from the side where the alkyl group is the closest, which is closest right here. 1, 2, 3, 4, 5, 6, 7. Done. Let's look into D. 1, 2, 3, 4, 5, 6, 7. D is also 7. So now this is something we have to look into. You have where do we start numbering from? Again, we start numbering from the side where the alkyl group is the closest. So this is 1, 2, 3, 4, 5, 6, 7. Done. Now the question is, which of these are the correct options? Also, let's count the total number of carbons, right? So here, the longest chain wasn't being made. Here, let's also count the total number of carbons. This is 7. This is carbon number 8, 9, and 10. This is carbon number 8, 9, and 10. This is carbon number 8, 9, and 10, and 11. So C isn't the correct option. See, this is how you do A-level MCQs. There's no other way to it. You have to eliminate every single option. So C is incorrect. That's why in A-level students tend to face difficulty, because although the MCQs are pretty easy, they are very conceptual. You can't just select, all the options look the same. So you have to take into account every single possibility. In the first case, we eliminated B off. Why? Because it had the shortest chain. You weren't able to make the longest 7 carbon chain. So we eliminated B off. We eliminated C off because the molecular formula isn't the same. You have fewer carbons here, right? You have 10 carbons in compound T, whereas you have 11 carbons in compound C. So you can't, pick this out. And even here, this is 6, 7, 8, 9. You get 9 carbons here. So you could have eliminated B off because of that. So B and C are wrong. Now I have to select between A and D. And A and D both look like the correct options. Both A and D, you have 7 carbons in the parent chain, and you have substituents. So they both look as structural isomers for it. But let's start naming it now. Let's start naming it. You have a methyl on the second carbon, a methyl on the third carbon, a methyl on the fifth carbon. So this is 2, 3, 5 trimethyl. And what's the full name? Heptane. 2, 3, 5 trimethyl, and the longest carbon chain is 7. So 2, 3, 5 trimethyl heptane. And if I start naming this fella, this is what? 1, 2, 3, 4, 5, 6, 7. So you have the methyl on the second carbon right here. You have the methyl on the third carbon, and you have the methyl on the fifth carbon. So it is 2, 3, 5 trimethyl heptane, which is the same thing. These are not isomers. The names are the same, which means they are basically just ditto. They are the same thing. He's just drawn this and just flipped this off and drawn it. So these are both the same ideas. Both have the same names. They are both the same. So this is what makes D the correct option. If you want to name D, naming D is pretty simple. It's 2 on the second carbon, you have methyl. On the third carbon, you have ethyl meth, right? So it's basically 3 ethyl, because E comes first. 3 ethyl, 2 methyl heptane, if you wanted to name it, but you don't, right? These are MCQs. You don't have to name or do anything. Done. Easy, guys. Oh, it's getting me tired. Next question. A sample of pent-2-ene-4-ol, okay, contains all the possible stereoisomers of this compound. How many stereoisomers are there in this sample? So pent-2-ene-4-ol. Let's draw it. Pent means 5 carbons. 1, 2, 3, 4, 5. And he's saying that between the second and the third carbon, you have the double bond. See, that's why it's pent-2-en. En means the double bond. It represents the double bond. So 1, 2, 3, 4. Between the second and the third carbon, you have the double bond. That's why it's 2. Right? Between 2 and 3, you select the smaller number. That's why it's pent-2-en. So second and third, you have the double bond. And on the fourth carbon, you have the OL. So 1, 2, 3, 4. On this fourth carbon, I have the OH right here. So this is how the structure looks like. If you were to make it for yourself, this is how the structure looks like. Now he's saying how many stereoisomers are possible for this fella. Again, for stereoisomers, I'll have to look into geo, and I'll have to look into optical and geometrical, both. Let's first look into geo. Is geo possible? See, this carbon has a hydrogen and it has a CH3 bonded to it. This has a hydrogen and it has this fella bonded to it, which means there are 2 different groups on each of the carbon in the double bond, which will therefore exhibit cis trans. So this will exhibit cis trans isomerism. These will exhibit geometric isomerism, right? So this fella is going to give you stereoisomers. Now we have to look at optical. Can this give me optical? Is this a chiral carbon? No, it is bonded to 3 hydrogens. Is this a chiral carbon? No, it's the double bond carbon. No, is this a chiral carbon? No, double bond. Is this a chiral carbon? Yes, this carbon is bonded to a OH, it's bonded to a hydrogen, it's bonded to a CH3, and it's bonded to these many group of atoms. So this carbon in fact is a chiral carbon. This will exhibit optical isomers. And is the last carbon a chiral carbon? No, it's bonded to 3 hydrogens, right? So it's not this is not a chiral carbon. There must be 4 different group of atoms bonded to it. So this fella is a chiral carbon. And therefore, how many stereoisomers would you have? 2 to the power of 2. You have 2 sides, 2 to the power of 2. That gives me 4. And for C is the correct option. Next, how many more MCQs are left for 2024? My god, 17 MCQs in total. Can I get a 2-minute break, guys? I'm tired. Next, question 13. Which alkene shows geometric isomerism? Which alkene shows geometric? Again, this won't show geometric isomers because it isn't bonded to different groups. Each carbon in the double bond must be bonded to 2 different groups. Remember this. Each carbon in the double bond must be bonded to 2 different groups, right? So this is bonded to 2 hydrogens, therefore A is wrong. This fella is bonded to a hydrogen. This carbon is bonded to a hydrogen and a CH3. This carbon is bonded to a hydrogen, and this entire fella, these are different groups, and therefore B is the correct option. If you look at this fella, this carbon is bonded to 2 hydrogens. Again, each carbon in the double bond must be bonded to 2 different group of atoms. So this is wrong. If you look at this D right here, this carbon is bonded to a CH3 and another CH3. So again, this carbon is both bonded to the same group of atoms, not different. Therefore, D is also wrong. So B is the correct option. Shukara, an MCQ which was quick. The alkene CH3 whole twice undergoes free radical substitution. You'll learn that later on with chlorine. Right? And he's saying no CC bonds are broken in this reaction. How many isomeric products, including positional and optical of molecular formula C5H11Cl can be formed? Right, now you haven't learned free radical substitution with chlorine, but just imagine that this is a structure and you'll have to place chlorine on either or, right? So I'll draw the structure for you. CH3, CH2, CH, and then you have 2 CH3s like this. CH3, CH2, C bonded to a H and bonded to 2 CH3s. Right here. And if you want to draw the skeletal for it, this is how the skeletal would look. See, this is the longest chain, and the skeletal would look like this: 2, 3, 4. And on the third carbon, you have this CH3 right here. So this is how the skeletal will look, and I prefer skeletal. It's easier to visualize, right? This is my skeletal. Now, free radical substitution with chlorine means you'll have to plug in one chlorine, right? So you can either plug a chlorine here, 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 here. These are all the sites for chlorine. It can come here, it can come here, it can come here, it can come here, it can come here. Now, let's plug it on all these places and see where you'll get how many isomers you'll be able to get, right? So 2, 3, 4. This is it. 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 I have to make how many possibilities? 1, 2, 3, 4, 5. 5. So I'll make one more. 2, 3, 4. This is it. Right? Tuck, 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 tuck. So let's put the first chlorine here on the first one. This is the first possibility that can take place. It doesn't matter how you put the Cl. I'll just put it like this. The first possibility. The second is to place the chlorine here. That's the second possibility. The third is to place the chlorine on the middle carbon right here. That's the third possibility. The fourth is to place the chlorine on this carbon right here. That's the fifth possibility. And the fourth possibility, sorry. And the fifth possibility is to place the chlorine here. Now check it out. Start naming it, please. Start naming it and numbering it. Even if you don't name it, start numbering it. It'll make your life easy, right? So you start numbering from the side where the functional group is the closest. The Cl is the closest. 1, 2, 3, 4. This is what? 1 chloro and 3 methyl. 1 chloro, 3 methyl, right? So this is this fella. This fella is what? 1, 2. It's 2 chloro, 3 methyl. So you can even, it's not necessary that you write it. I'm just writing it so students who are just looking into this PDF can also, get advantage of it. So it's 2 chloro, 3 methyl. So these two are 2 isomers. Next, this fella right here. This fella. I don't even have to name it, but if you look at this fella, it has a CH3 right here and it has a CH3 right here. It's 1, 2, 3, 4. Again, it's 1, 2, 3, 4. And if you want to name it, it's you start numbering from the side where the functional group is the closest. If I were to name it, it's what? 2 chloro and 2 methyl. 2 chloro, 2 methyl. Butane, right? 2 chloro, 2 methyl, meth, eth, pro, butane, right here. Butane. Nobody cares. Now, some of the students might think, sir, this is a chiral carbon. It's not a chiral carbon. Why? Because see, this carbon is bonded to a CH3 and it's bonded to another CH3. So it can't be chiral. Yes, it's bonded to a chlorine and it's bonded to these group of atoms. It is bonded to a CH3, but it's bonded to 2 CH3s. This fella is also a CH3 and this fella is also a CH3, and you can check it out. See, this carbon, when a chlorine comes here, this is a CH3 and that's a CH3. So it's not a chiral carbon. You just have to keep your eye out for it. Please do not mark this as chiral carbon because this is a CH3 and that's a CH3, right? So this is an isomer, but not a chiral carbon, right? Not a chiral carbon. Next, let's look into this fella. 1, 2, 3, 4. So again, This is carbon 1, carbon 2, carbon 3, carbon 4. What do you get? You get 1 chloro and 2 methyl butane. Done. And similarly, if you start numbering from here, 1, 2, 3, 4, this is my long chain, 1, 2, 3, 4. What do you get? You get 1 chloro. On the first carbon you have chloro and 2 methyl, and you've already discussed that, right? 1 chloro, 2 methyl, these two are ditto, they are the same. Now let's look into chiral carbons. We already discussed that this carbon is not a chiral carbon. Why? Because you realize that this carbon is bonded to Cl and this, but it's bonded to 2 CH3s. There aren't 4 different group of atoms, so this isn't chiral. Similarly, this carbon right here, this fella, it's bonded to this carbon is bonded to a CH3, but it's bonded to this fella, but it's also bonded to 2 hydrogens right here. So this is also not chiral. This is also not chiral. This carbon is the same as this things. The remaining carbon is this fella right here, 2 chloro 3 methyl. And if you look at 2 chloro 3 methyl, is this chiral? Absolutely, this is C. This carbon is bonded to a chlorine atom. This carbon is bonded to a hydrogen atom. This carbon is bonded to a CH3, and this carbon is bonded to this group of atoms. I can even show it to you. This carbon is bonded to a Cl. This carbon is bonded to a CH3. This carbon is bonded to a hydrogen, and this carbon is bonded to these group of atoms. So you have 4 different group of atoms. Therefore, this is a chiral carbon, and therefore it will exhibit optical isomerism, and it will give you 2 isomers. One isomer's name we've already written. The other one would be the superimposable. Because see, this carbon is bonded to a CH3, and this is CH2Cl. It's not a CH3. It's carbon bonded to 2 hydrogens and Cl. If you want to show it like this, you can even check it out. This is CH3 bonded to a CH2 bonded to a C, which is bonded to a CH3, which is bonded to a hydrogen, and it is bonded to a CH2Cl. My carbon, it's not CH3, it's CH2 bonded to a chlorine as well. So this is what it is, an optical carbon, chiral carbon, and this will also exhibit optical isomerism, right? So you also have 2 optical isomers here. So 2 isomers here, 2 isomers here, that's 4, this is 5, and this is 6. So you're going to end up with 6 isomers. These two are the same things, right? So 2, 4, 5, 6, right here. So what is the correct option? The correct option is C for salts. I'm tired now. I'm tired. Next. Okay, MCQ number 15. The diagram shows the structure of naturally occurring molecule of cholesterol. Okay. Student X stated that there are 17 carbon atoms in 4 rings. First of all, let's check this out. 17 carbon atoms in 4 rings. Are there 17 carbon atoms in 4 rings? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And a lot of students would say, yes, student X is correct. But he's saying they all lie in the same plane. Do all the carbons lie in the same plane? No, they don't. No, they don't. Because see, every carbon, most of the carbons are sp3 hybridized. If you check this out, this carbon is bonded to 2 hydrogens, and this bond, they're all sp3 hybridized, most of them. And sp3 hybridization means what? They are tetrahedral. And tetrahedral means what? One is going to be into the board, out of the board. You have wedges, into the board wedge, out of the board wedge, into the board this. So they won't all lie in the same plane. So student X is wrong. So student X isn't correct. Both student X and Y won't be correct because X is wrong. Now between B and D, we have to check out which one is correct. B and D. Student Y stated that the molecule displays cis-trans isomerism at the CC double. Oh, this is not a part of your course. Why is this tested here? I am highlighting it for myself. This shouldn't be tested here. It's not part of your course. But okay, fair. Student Y stated, now I'll tell you, because it's tested, I'll tell you some ideas about it, but it's not a part of your course. Neither in AS level nor in A2 level. Where what the hell is the examiner doing? Khair. So he's saying which student is correct right now. He's saying student Y stated that this molecule displays cis-trans isomerism at C double bonded to C double bond right here. C double bonded to C right here. Will it exhibit cis-trans isomerism? Now, what all teachers would have taught you, and what I myself have taught you, if there are 2 different group of atoms on each of the carbon in the double bond, they will exhibit cis-trans isomerism. And if you check this carbon out, this carbon is bonded to this entire fella, and this carbon is bonded to this entire fella. So they are different group of atoms, absolutely. So this carbon will exhibit, this carbon checks out. And look at this carbon is bonded to a hydrogen and it's bonded to this entire group of atoms. So it's bonded to two different group of atoms, and therefore this will also this and this, both these carbons check out, and therefore it should exhibit cis-trans isomerism. But in this particular question, they won't. Why won't they? It's not part of your course. I don't know why the examiner has tested it. The reason why it won't is because the double bond is present in the ring-like structure. The double bond, when a double bond is present in a ring, you realize that there is something known as the ring constraint, which isn't a part of your course. Ring constraint basically क्या होता है? What is a ring constraint? Basically what happens is, in smaller rings, like a 3 carbon ring, a 4 carbon ring, a 5 carbon ring, a 6 carbon ring, a 7 carbon ring even, and this is a 6 carbon ring, 1 2 3 4 5 6. So in smaller rings, which are 3 4 5 6 carbon rings, what happens is that the ring structure, it itself restricts how far apart these groups can be. This group, how far apart this can be, how fast apart this can be. The structure becomes locked. And what happens is that once the structure becomes locked because of the double bond, and inside the ring structure, the substituents which you have, all the groups that you have, they are bound to be the cis isomer. They are bound to be the cis isomer. You can never have a trans isomer here. They will always be, cis isomers, which will be shown to you guys. Now there are multiple reasoning to it. Ring constraint isn't a part of your course. What exactly a ring constraint is? It basically means that the ring is a rigid structure. Unlike an open chain alkene, the ring is rigid and the atoms are locked into a fixed geometry. And so if a double bond is present inside the ring right here, if the double bond is present inside the ring, it fixes the relative positions of these two alkene carbons. It fixes their positions. And so that prevents rotation or flipping of substituent. You can't even flip it. You can't flip it. So this particular idea is not part of your course. And so this ring forces the double bonded carbons to be cis. Trans can't exist here. Because if trans were to exist, there would be severe bond angle distortion. It would be, in some cases, you would even tend to break the bond because of the structure being too huge and this ring being locked inside one position. So normally cis-trans isomerism would exist, but in this particular case it does not. And if you want to rote learn this, because the examiner has tested this and this is not part of your course, it's an extremely advanced level concept. If you want to remember this, just remember that if there's a double bond in a ring structure, even if there are different group of atoms or different atoms bonded to each of the carbon in the double bond, it will not exhibit cis-trans isomerism. It will not exhibit geometric isomerism, right? But the idea is only limited to small rings, by the way. So ab itna ho gaya, so let me even tell you this. This is only limited to small rings. You can have rings which are like which have 8 carbons and so on and so forth. They will exhibit cis-trans isomerism, even if there's a double bond. They will therefore exhibit cis-trans isomerism. But this concept is not part of your course. I don't know why it is tested. And probably a lot of teachers would have gotten this wrong. So which one is correct? It's neither X nor Y are correct. This MCQ should not have been tested. I've highlighted it for myself. I will discuss it with the teachers as well as Cambridge. Email karunga Cambridge ka jo ek examiner hai, I know that person, so I'll ask him why was this tested. Right? Maybe they have admitted their mistake, maybe. So yeah, in S level you might see something like this even. खैर एक MCQ तक कुछ नहीं होता, रहने दे. Next, the drug cortisone has the formula shown. In addition to those chiral centers marked by steric, how many other chiral centers are present in cortisone? How many other chiral centers are present? You have 1, 2, 3. Let's look at the junctions. Look at this junction right here. This junction, it has a CH3. It's this entire group, that entire group, that entire group. So this is a chiral carbon. I'll circle it so you can see it better. Next, look at another junction. This is a junction. Oh, they've already mentioned. This is a junction. Always look into the junctions, because all the carbons right here, they're already CH2. So I look into this junction right here. This entire fella is bonded. This fella is bonded to this entire stuff. Is bonded to this entire stuff, that entire stuff, and a CH3. So this is also a chiral center. If you look at this junction, there's a double bond. So double bonds can't exhibit optical isomers because 1, 2, 3. There are only 3 different group of atoms. Similarly, look at this junction right here. This junction is also a chiral carbon. Why? Because it's bonded to an OH, it's bonded to these group of atoms, that group of atoms, and this group of atoms. So they're all different. So 1, 2, 3. Any other chiral center that you guys can see? No. This is already marked, that's already marked, that's already marked. This can't be because of double bond hai. And yeah, other than that, I don't see there are any others. So 3 chiral centers, 2 to the power of 3, 8 isomers, right? How many other chiral centers are there? 3. 3 other. Next. Oh, finally, last question of 2022 set. Structural isomerism only should be considered when answering this question. Okay. How many compounds with molecular formula C5H11Br are primary haloalkenes? Now, I haven't taught you guys primary haloalkenes, but you guys have seen primary carbocations, which are what? Which are carbocations bonded to an alkyl group. So, primary haloalkenes would be those in which you have one alkyl group being bonded to this particular carbon which has the halogen atom. So, there's only one R group right here. So, how many primary haloalkenes can be there? Let's check it out. C5H11Br, right? Let's use the CAN method. And can I use chain as well as position? Yes, he thinks you can use structural isomerism. So chain as well as position. Don't talk about stereo. So let's do this, fellas. Let's do this. You have 5 carbons, right? So 2, 3, 4, 5. Then you have 2, 3, 4. Then you have 3. And I won't go below this. Done? Now, I have a BR, which I have. BR is my add-on for the 5 carbons. So 2, 3, 4, 5. The first BR, if I add it on here, that makes sense. Because see, now this is a primary haloalkane. Why is this a primary haloalkane? Because this carbon is only bonded to this alkyl group, only one alkyl group. The other bonds are with hydrogens. This carbon is bonded to 2 hydrogens, 1 Br, and only one alkyl group. So this is in fact primary. Done. Now let's change the position. If I take the Br and place it here, this would make it secondary, but I'll still do it. 2, 3, 4, 5. I'll place the Br here. Now this is a secondary haloalkane. He just needs primary. Why is this secondary? Because this carbon is bonded to one alkyl group and the other alkyl group. This carbon is bonded to 2 alkyl groups, hence secondary. Right? If you place it on the third one, right here, this carbon is now bonded to this alkyl group, and that alkyl group again is bonded to 2 alkyl groups, hence secondary, not primary. And we bond it right here, it becomes the same thing as the first fellow. So first of all, in this particular structure, I only have one primary. Now let's go on to 4 carbons. 4 carbons would mean that you also have an alkyl group. So what I'm going to do is 2, 3, 4, and I'm going to first place the alkyl group right here. And this is my locked structure. If I place the alkyl group here or here, it doesn't really matter. So 2, 3, 4, I can place the Br 1, 2, 3, 4 in 4 places, right? So I'm going to make this structure 4 times. Done. Now I can place the Br right here, and this is a primary haloalkane. Why? Because this carbon is only bonded to one alkyl group. This carbon is bonded to one alkyl group and 2 hydrogens, so this is primary. Then I can place the Br right here. This is a tertiary haloalkane. Why? Because this carbon is bonded to an alkyl, no hydrogen whatsoever, tertiary, so we don't need this. Next, I can place the Br right here. It's again a secondary haloalkane. Why? Because this carbon is bonded to 2 alkyl groups, so secondary. And then I can place the Br here. And fun fact, let me just place it here. Fun fact, this fella is different from this fella. See, this, if you start naming it, numbering it, 1, 2, 3, 4, this is what? This is 1 bromo 2 methyl butane, right? 1 bromo 2 methyl. And this fella is 1, 2, 3, 4. This is 1 bromo 3 methyl butane. So this is also primary. Why is this fella primary? Because the carbon is only bonded to one alkyl group, 2 hydrogens and 1 Br. So you have primary here and you have primary here. Done. So you have 1, 2, 3. Next, last fella. These 3. Now first of all, you have to place the 2 CH3s, 2 alkyl groups. You have to place the 2 alkyl groups such that the chain does not change. So 1, 2, I'll place it here, because if I place it on the terminal carbons, we've already discussed this longer chains. So placed it here. Now I can place the Br. I can't place the Br on the middle carbon, because it will already made 4 bonds, I can either place it here or here, and both will give me the same answer, right? If I place it here or here, both are the same. So I'll place the Br right here. If I place it even here, both the names are the same, they're the same structures. Let me use a different color for placing the Br. What's the name? 1, 2, 3. And this is also a primary haloalkane. Why? Because the carbon which has the Br is only bonded to one alkyl group. That's it, this entire fella. So what's the name for this? If you want to name it even, it's what? It's 1-bromo 2,2-dimethyl methethropropane. That's the name for it. So how many primary haloalkanes do I have? 1, 2, 3, 4. 4. And so A is the correct option. Done with the 2024 set. Any questions, guys?